Okay. All right, so input, say it. Output. Should be able to input, output, and get a graph of this, and we've already done this in chapter 1. But now it's chapter 3, which is all exponentials and then logarithms. An exponent, and even the logarithm graph, we stuck in the book of functions that we had. You remember that book, right? That little book with at least 7 of them, but there were 12. But I said no 7 of them, and this was definitely one of the 7 because of input output. And you better get this figured out, all right? Because they're going to hear this a million times. Like, what's 2 to the 0? 3, 2, 1, go. 1. And hopefully you heard some of those other people, and more people were able to say 1. It's a rule. Anything to the 0 power is 1. No big deal. There's a reason behind it, and I don't care for the reason right now. The reason's done. And then, sorry, I got to make this bigger. I was thinking in smaller senses what the key components are. So we're going to do 1, 2, 3 input output. I was going to say you're tardy. You're not even in my class, so he just left. He already picked up his field pass, but then he had something else. Yeah, he's gone. You want me to just keep it and throw it out or no? Yeah, just throw it out. Okay, and then what happens when I plug in 1 for x? Well, I get y equals 2 to the first. What's 2 to the first? 2. I'm not going to insult you by asking that question. All right, and then what happens when I plug in 2? Well, that's 2 to the second, which is 4. And what happens when I plug in 3 for x? That's 2 to the third, which is 8. So this input-output, I've been having you visualize. Now I finally wrote it. You know, we should know how to do this without any problem. But now we got an issue. What's 2 to the negative first? Now this is where the stuff hits the fan, so to speak. Get a whole bunch of different answers for this from students. What's 2 to the negative first? 3, 2, 1, go. 1/2 or 0.5. Interesting. But did you use your calculator for that 0.5? No. Okay, good. So you turned 1/2 into a decimal. But really, what it is the flip thing. This becomes 1 over 2 to the first. That's the negative exponent rule. There's a reason why this happens. The reason has to be done at this point. You have to get it memorized and know. All right, and I've covered those reasons before, but it was all the way back in August. Remember, this is how we started in August with these exponent rules, by the way. 2 to the negative second is 1 over 2 to the second, so that's 1/4. Oh, this is getting annoying. These look like, as I plug in negative numbers, these fractions become infinitely smaller. So how do we show that in a graph? We use something that starts with an A. 3, 2, 1, go. Asymptotes. Okay, so that's why we discovered that we do have an asymptote for this graph. And you know what? I'm only going to graph 1, 2 and 2, 4. So there's the exponential taking off. 2 to the third, 8, 2 to the fourth, 16, 2 to the fifth, 32. Boy, I plug in 5 and I already have 32 as a y value. This thing is growing fast. That's exponential growth. But then when I throw in negatives, this is where the fractions come in, and then we can understand the asymptotic behavior. So we draw that boundary because the left side of this graph is annoying to draw closer and closer to the x-axis. We'll just put a dotted line there. That's true. That's why we do asymptotes. So I don't have to do that anymore. Okay, and then I'm going to add a new function here, doing this a little different than last hour. Even though we did do it last hour, I just kind of did it in reverse. What happens when I say fractionally, like 1/2 raised to the x? What kind of picture do we get with that? Input, say it. So we're still going to throw in 0. Anything to the 0 power is 1. But now what happens when I plug in 1, 2, 3? Because of timing, because this is a high-level math class, we're just going to mentally evaluate. 1/2 to the first is 1/2. Uh-oh. 1/2 to the second. I kind of kept wanting to show that original one there, but 1/2 to the second is 1/2 times 1/2, which is 1/4. Oh, this is where we get the little numbers. That took forever. My pen won't write. To the third, now I get 1/8. This is where I get the small numbers. And then what happens when I plug in -1, -2, -3? Flip. Y equals 1/2 to the -1st is actually 2 to the 1st. I don't know why I put a negative, sorry. 2. Now these numbers start getting large. 1/2 to the -2nd is 4. 8. Because it flips 1/2 to make it 2, and then that becomes 2 to the 3rd. So this graph looks a little different than the other one. This one, 0, 1, still the point, but now these are where the small values are. And this is where the values are larger. And again, I'll just do -2, 4 to show that. Still have a horizontal asymptote at y equals 0. So hence there's the difference between those two graphs when you manipulate the bases a little bit. All right, and then I'm going to show you a general form for this. All right, but we proved this through input-output, the two different graphs that we have here. As I read left to right, this one grows. As I read left to right, this one decreases. Another word for that is decay. Okay, so now let's go to our format of here's what we need to know from section 3132 as far as these graphs are concerned. And then a couple other things that we'll put together. This first graph, this is when your base is bigger than 1. This mirrors the 2 to the x graph. This is when b is greater than 1, we can get this scenario happening. All that would happen with our chart of values, if you could just think about it as you write this down for your schematics about what I need to know here. If I made the base 3, 4, or 5, it just gets steeper. Like, think about that chart of values. 5 to the 1st is 5. And then 5 to the 2nd is 25. Oh my gosh. I increase the base, the graph just starts taking off quicker. But it's still going to look kind of like this. It'd be 1, 5 here instead of 1, 2. That's the only difference. And then this one more mirrors the y equals a half x raised to the x, not half x. This is when b is between 0 and 1, a fraction between 0 and 1. Then we get what looks like a decay. As a matter of fact, I'm going to write these down here. This one is a growth. This one is a decay graph. We're going to ask that a lot when we deal with some other components of this section. Just kind of wanted to introduce, really big on the graphing, input, output, and then some more things are going to happen in 3132 that extend beyond graphing. Okay, and then I'm going to show this to the right, but hopefully it's not too small that you can't see it. For both of these cases, the domain is all real numbers. Ooh, what a naughty way to write that. We should be writing that as negative infinity to infinity. This was on our, book of functions. If you pulled that old book out, this is the stuff you would see. The range is 0 to infinity, 0 with a parenthesis. This graph never makes it to 0. You can't raise 2 to a power and get 0 as a result. You can get very close, but not quite. All right, so that's what we have to understand there. There is no symmetry, none of that. It is bounded below, if you want to remember that. There's a boundary below. I was never a big fan of caring about that. No extrema, but we do have that horizontal asymptote, no vertical. So if you want to take a moment to write that, go for it. I know why that's there. I know what they did. The little cursor there from a screenshot. Don't worry about what that is. Wearing blue today. And they got one of my favorite Star Wars shirts, the originals. Sorry. Anyone wear blue on purpose today? Did I ask that as you walked in? No one knew about it. Down syndrome, you're supposed to wear blue today, but it was not really thrown out there too much for us to know. Okay, all right. These are tied together. So just remember your limit notations. This is a growth. What are our limit notation situations for that? Remember X finger, Y finger. As my X's increase, input, output, what do my Y's go to? 3, 2, 1, go. Infinity. As my X's go off to negative infinity, where's my Y finger being limited to? 0. Okay? So we should know that at this point, this is not a new concept. We've been talking about limit notation since August. And it's not a new concept walking in. Okay, so knowing those, and actually that's in our book of functions as well. But now we're really going to focus on graphing exponents and then later logarithms, and do more stuff with them. So that's going to happen today. And the second one, the decay graph, which I guess I'll color that in blue. Still see it through this blue here. Exponential decay. Decay means decrease, or it goes down as you read left to right. So that means left to right, the y's go down or decrease. So decrease, decay. Synonym. X finger, Y finger. As I throw in positive x's really big, what do the y's get limited to? 3, 2, 1, 0? 0. I accidentally said that during my countdown. And then as x gets negative, y gets positive large. All right, so those are flip-flopped. Everyone okay so far? And this boring Monday, right? That's why I wanted to keep it simple. My poor math tours, I did 45 minutes of notes of something kind of brand new. They shouldn't complain about it too much. Okay, now we're going to play a game. Increase or decreasing. Exponential growth or decay. No, come on now. In 3, 2, 1, what is this one? Go. It is decay if you take Matt's answer. Come on, you know the rules. And then it does ask you to do the limit notation. What would the limits be then? It's the blue one. Those are the limits. Don't, come on. I don't want to have to redo this over and over and over again. Okay, now wait, everybody. Let's do it in 3, 2, 1. Okay, number 2, growth or decay. 3, 2, 1, go. Growth. And then what would the limits be? It'd be the yellow limits. I mean, let's not be ridiculous here. Thinking about this, though, this would really take off. I plug in 1 for x, I get 8. I plug in 2 for x, I get 64. 2 comma 64. That's an insane growth there. Blah 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 blah. Number 3. Oh, it's gone. I guess I might put my finger there. Growth or decay. 3, 2, 1, go. It should be that fast. Growth or decay. 3, 2, 1, go. Growth or decay. 3, 2, 1, go. Oh, I think I heard more growths. Watch this. This 0.25 is actually 1/4. First of all, let's think about that for a second. I know fractions sometimes we don't like them. And then did you know that this is the same as 1/4 raised to the negative first? Raised to the x, we can kind of think of it that way, splitting up the exponents through the multiplication property. And then everybody, what's 1/4 to the negative first? 4. This is equivalent to this. So growth or decay, 3, 2, 1, go. Growth actually in disguise. So this original question is a growth situation. The power of the negative exponent rule. All right, so you should get this one right. Growth or decay, 3, 2, 1, go. dk. Fastly written, using all of these steps in here, this actually equals y equals 1/5 raised to the positive x. That is true. So this is actually a decay. Good little question just to think about before you proceed forward. And like getting into the thinking of graphs. Okay, so I know I kind of went over those really fast because I don't think we need all of them to like write formally as notes. The last two are very good though. Okay, very good to think about. Now, to really think about graphing, and I want to get rid of this one little thing here so you don't see it anymore. We got to remember transformations because that's what we're going to end up doing here. Then tomorrow we'll build off of this. I know the beginning of my notes, probably tomorrow we'll start with this again. We know, and that's what the point of the book of functions were, you actually graphed this already. You already graphed exponentials. I had you graph one on the chapter 1 test. Through input, say it, output, you had to do a chart of values and know how that chart actually worked out. Okay, but then it's good to think about these things. Like a negative on the outside, that represents a flip over the x-axis. I don't have one of those in my notes today. We should make sure we do that tomorrow. I hate having a values with exponentials, but those are stretch shrink values. I wish they kind of leave those out. The book loves putting those there. That's why I do a lot of worksheets in this for graphing. But then my worksheet generator isn't so great either. The base that you have here does matter. All right. Don't think of it as a stretch or a shrink though. Just the base. If the base is bigger, the graph does take off quicker. If it's between 0 and 1, then you got to be careful that it's decay. But then we just dealt with this. That negative on the inside, that orange color, that's a y-axis reflection. Here, look at this. We can think of this as a y-axis reflection of the 5 to the x graph. The 5 to the x graph increases. But with that negative on the inside, it actually flips it over the y-axis and makes it a decreasing 1/5 to the x power. So if you just think about that negative on the inside, it's a y-axis reflection. If you can think about both of these graphs compared to the 5 to the x graph. But anyway, don't want to overload the brains giving you too much information. Negative on the inside of the function means y-axis reflection. And then you better get this right. Minus c plus d. C on the inside is right-left shift. Opposite. Up-down shift, same. If I see x minus 3 on the inside, that means 3 rights. If I see plus 4 on the outside, that's 4 up. Because that's the way I would think about those things. And then this was just the point of, you know this from actually even last year when you did quadratics too much. Maybe even your sophomore year. Okay? So we know and recognize this. And as you write this down, I know this is not exponential, this is a quadratic, but all functions get affected the same way. So what's this negative on the outside do? 3, 2, 1, go. X-axis reflection. Stretch or shrink on this 2. 3, 2, 1, go. Didn't go so well. That's a stretch because it's bigger than 1. Okay, you better get this right. This is 3 to the 3, 2, 1, go. Ooh, I heard a couple different things there. That's 3 left. We got to remember opposite on the inside. This does move it 3 left. Or what do I have to plug in to make this 0? That's how I approach that. What number do I have to plug in there to make this 0 on the inside? -3. -3 is 3 to the left. All right, that's the way I approach those transformations, input, output. And then what's the -4 do? 4 which way? 3, 2, 1, go. Down. You better not get that one wrong. 4 down. So you've done this before. We've practiced this. Okay, so then the teachers last year did a real nice thing. They kept this simple. They kept this simple to simplistic questions like this, but I'm still going to input, output. When I see your graphs, I better see 3 discernible points. All right, and I'll tell you what those 3 points are as we do these two examples one at a time. So let's focus on this one first, even though you could probably kind of see the other one. Let me get myself in front of that one. There you go. Can't see it. Nice. 2 to the x minus 1. First of all, what should that x minus 1, what should the minus 1 do? Which direction? 3, 2, 1, go. To the right. But really what it does is it dictates what I'm going to input-output, that mean Mr. Samuelus. And I don't really necessarily need the chart. I would expect you to be able to do this in your head. This is why I don't write them down. Like, for instance, I'm going to plug in 1 for x first. Why? Just what I said before. What's 1 minus 1?
0.
What's 2 to the 0 power? 1. So 1 comma 1 is my first critical value. This is the 0 power rule point. This is the first point that I should be graphing for any exponential. Because then after that, the discernible points are right above and below that, or right next to it. So if 1 is the 0 power point, then I go 1 below and 1 above for the other 2 points. Then I can start seeing some asymptotic behavior with one of them. Well, here it is. What's 0 minus 1? Negative 1. What's 2 to the negative first? Well, I hope you can survive that. That's a half. This is where we're having the problems. These simple input-outputs. Being able to get these values. And then this is a signal to me that this is where the asymptote is. This is the start of the asymptotic behavior when I start getting those fractions. When I go past this, 2 minus 1 is 1, 2 to the first is 2. This tells me, okay, if I keep going this way, the numbers are going to start increasing. When I keep going this way, the numbers are going to start approaching 0. And that is the number that they are approaching. So that's why 2 comma 2. I'm going to go ahead and draw my asymptote because this did not get moved up or down. So the asymptote is also at y equals 0, just like the parent. So not a lot happened on this one. If you wanted more shape to your graph, feel free to plug in some more things. 3 comma 4, 4 comma 8 if you wanted. Don't go the other way because those are messy. All right, and then this one, this is the idea that we have that y-axis reflection. Okay, so here's the right one. This point, it doesn't really show up too well, but it is a moved right one. This one is the y-axis reflection. Oh, and I forgot to do domain and range for these questions. They're not really special. For both of them, they're going to be the same. So I'll write that at the end. But I am going to start with 0. Because 0 negative is still 0. And then 2 to the 0 is still 1. So there was no change here. You still have 0, 1. There was no right, left, up, or down shift. You don't see that in the equation anyway. So a little too simplistic probably of a start. And then I'm going to go 1 and negative 1. Right above and right below. But when I plug in 1, it turns negative before I take 2 to that power. So now this is 2 to the negative first. This is a half. So this is why this looks like a y-axis reflection. And then when I plug in negative 1, negative 1 is 1. 2 to the first is 2. This changed for this being where the graph takes off this way, and then it approaches an asymptote here. So compared to the parent, this is a y-axis reflection. This should have been looking like this, but now it's flipped over the y-axis if you had to describe the transformation. Now, domain and range for both are the same since not much happened here. Domain for exponents are always all real numbers. There is nothing, you can take any number to any power. The range, though, is limited, just like the parent, by that asymptote as a boundary there. Okay? Everyone all right? I don't think this is hard. And actually, it's 100% review. I know people hate when I say that. I don't know how that's an illegal statement at this point. We've did this quite a bit with chapter 1. By the way, what's the plus 4 do? 3, 2, 1, go! Up 4. So this does start affecting some things. I wish I could add some more stuff to this, but I didn't go too crazy in the notes. Probably should have went a little bit more. And I am going to do input output. What do you think the first number I'm going to plug in is? 3, 2, 1, go. It's still 0. There was nothing tricky about that. My bad. I'm still going to plug in 0, and I don't know why I made the chart this big because I only need 3 points. But now 3 to the 0, and they're just saying here's the parent function with a base of 3. What is the new one compared to it? We already set it up for. I'm not writing it. But now let's evaluate and graph this. 3 to the 0 is 1, but 1 plus 4 is 5. This is the most important point to track. 0, 5 now is my 0 power point. This is the one where everything special happens for the exponents. The asymptote's very close, right? And that's why we need this helps. This helps with our case. And then -1 and 1. Fine, I'll write -1 when we do g of -1. G of -1 is 3 to the negative first plus 4. 3 to the negative first is 1/3. 4 plus 1/3 is 4 1/3. That tells me that the plus 4 also moved the asymptote up 4. What my y values will approach are now 4 as I plug in negative numbers, not 0. So that's how we use the plus 4. Piggybacked off of what I see in the chart of values. So that is why it's still important to show me 3 discernible points, because it also puts everything together. Then 3 to the first is 3. 3 plus 4 is 7. So 1, 7. This is where the graph starts taking off. Now for this one, let's put domain and range below. Of course, the domain is, oh my gosh, that was a brain mishap. -infinity to infinity. The range, though, is 4 to infinity. And I shouldn't have to ask someone that. I haven't had individual grabbing the calculator, getting students thing. Should do that. And then limit. I guess I haven't written these in a while, but I wanted to leave a chart of values over here. So the limit of f of x, I'll only do it on this one. We won't do it on the next one. As x approaches infinity. What's the answer? 3, 2, 1, go. Infinity. And then the limit as x approaches negative infinity of f of x. I forgot to say that part. What's the answer to that one? 3, 2, 1, go. 4. You got it. It approaches the asymptote as you go big negatives to the left. So those questions become a little bit more special with an exponential. Okay, one more graph, and then I'll show you the last part of this. Wish I had more that put it all together, like a couple things happening. I will ask you this. What if you weren't thinking about transformations and you just thought about your chart of values? What is the, I don't know why I'm making the chart so large, because I only need 3 points. What's the first point I'm going to plug in? 3, 2, 1, go. 5, not 0. Think about it, if you plugged in 0, what would you end up with? 3 to the 5th. That's a huge number. So that's where the graph's already taken off. That's not by the asymptote. It's actually 5. You want to locate the 0 power thing. So it's 5. 5 minus 5 is 0. 3 to the 0 is 1. Interesting. 5, 1. So you know what that did? It moved 5 to the what? Which way? Right. And that may blow your mind because you see a positive 5 on the inside. Here's the reason. This is actually g of x equals 3, trying to write this large, to the -1 times x minus 5 power. Take out a negative, and now what would this be? 5 to the what? 5 to the what, everybody? 3, 2, 1, go. What? You guys don't know yours? Minus 5 on the inside is 5 which direction? Left or right? 3, 2, 1, go. Right, and I just moved right. How do we not answer that? Look at this. This is 5 places to the right. That's where the 5 right came in. Okay, calm down, Mr. S. It's a Monday. And then what does this do to the graph? A negative on the inside, an x-axis or a y-axis reflection. 3, 2, 1, go. Y-axis. So what that means is 3 to a power should increase. Well, this is going to decrease. And I'll prove it with the chart of values. So 4 and 6. Look at what happens when I plug in 4. It's easy. 5 minus 4 is 1. 3 to the first is 3. 4, comma 3. 1, 2. So I'm coming this way. And then 6, I got it. 5 minus 6 is negative 1. That gets me 1/3. Got it. So I still have this asymptote here, but the graph decays or decreases to this. So that would be a reasonable drawing of it. So I'm still looking for these 3 discernible points. The one in the middle is the 0 power point. And then go one above, one below to see where the asymptote behavior is. When you get those fractions, that's where it happens. Okay? And then you go from there. All right. So good enough with that. Now I'm going to do this section, which is the first 6 on your worksheet that I gave you. Just a little introductory to exponents. 3.1 has a lot of stuff, but I think I do want to do what we did last year and combine what the next parts of this section is. The ability to come up with exponential equations from given information. And we'll hit this again later, solving exponents, when we introduce logarithms, which you have seen before, but students need to see it twice. So I won't use the, you've done this before thing with logarithms. They need to be looked at again. But here's how we're going to solve these. It's by getting equal bases. And I do have a little bit of time for this. I do want to write some crazy three equations here. You ready? You guys ever heard of sine, cosine, tangent? We're going to solve a trig equation right now. Sine of 7 equals y. My pen. Equals sine of x. Hey everybody, what does x have to equal? 3, 2, 1, go. 7. I mean, doesn't it? It's all about, it's kind of like just like, well, I don't know what sine is, and I don't know what solving an equation in trigonometry is. But by golly, I know by being a human being and just by matching, x would have to equal 7, then these would look exactly the same. Or all I'd have to do is plug in 7 for x, and then these would actually be the same two things, so yes, they'd be equal. Isn't that right? Hey, let's solve a logarithm equation. Log x equals log 12. Hey, everybody, what's x equal? 3, 2, 1, go. I mean, just by being a human being and just by matching, we'd have to say if I threw in 12 for x, then log 12 equals log 12. I don't even know what a logarithm is, but I know that's equal. Right? Yes or no? You're not doing the math here. It's not like I dropped the logs. You're just doing a little, this is what has to be the case. So here's what we're going to do with this. We're going to get 8 to be a base of 2 so that we can do the same concept. It's not like you didn't do anything, but, log of x equals log of 12. Basically, the only way that could be true is if x equals 12. I don't really have to look at logs anymore because, it's the same thing. And that's what the concept that I'm trying to get at you here is. When I get equal bases, then I can just drop the bases and make the exponents equal. By the way, what is 8? 2 to the what power? 3, 2, 1, go. Third, I hope I heard on this horrific Monday. I guess it's rainy and no one wants to talk. Before I continue and drop the 2's, And now if I drop the 2's and you think I did something mathematically, you missed the whole point of why I wrote the sine equals sine and the log equals log. All right, that was the whole idea. But here's my next question. What do I do with these exponents? Now that was in August. I talked to you about that. What do I do with these two exponents? Multiply is the answer. So before I drop these 2's, I am going to multiply those exponents. Okay, then I get worried. I get really worried when I write this next part. But remember, the reason I write this next part is because of the sine equation and because of the log equation. The reason I'm going to do this next is because this has to be true. If 2 to this power equals 2 to that power, the only way that could be true is if the powers equal. It's the only way that this could be true. Could have got a little bit more complicated with the sine equals sine and the log equals log. All right. Add 6 to both sides, x. Therefore, subtract 3 from both sides. And you get 7x equals 9, and this is possible. You get x equals, divide both sides by 7. 9/7. Okay? Then the next one, I didn't even get all that complicated with them. I was about to try to, and then I was just like, you know what? I think this is good. One more of these. What's that thing? Oh, the graph. I'll get rid of that for no purposes. 3 raised to the 7 minus 2x power equals 1 over 27. Can you put it on my chair? By the way, I didn't tell you guys, I didn't even look at your tests. I don't think I did. Kind of got a lot more things cleaned up on Friday. Did get all your homework. That takes some time to go through all your homework and grade those. I just made a management decision that I was going to do the test today and hopefully be done tomorrow. Get a busy night again tonight with the kids. Wait a minute. What's 1 over 27? 3 to what power? And that's the answer. I mean, that's numeric. You know your rules. You know what's going on. You know that this is 3 to the negative third. Because this is 1 over 3 to the third. That's what this equals. Better know 27 is a cube, 3 to the third. But then to get them 3 equals 3, that's actually 3 to the negative third. And then what you can do is drop those bases. Since they are equal now I can drop them and then go ahead and solve this remaining scenario. Well, I'll be darned. I subtract 7 from negative 3 and I get negative 10 and then divide by negative 2. I'll be darned if that actually ends up being a nice number. Okay, and then when we get into logarithms, we'll get questions where we can't get equal bases. And that's the whole reason why they developed logarithms, whoever they are. All right? But for right now, solving exponential equations with the ability to get equal bases can be done. All righty.